In this video we learn about gas diffusion and effusion. Right, gas diffusion is as simple to understand. This is the motion of gas particles through a medium. So for example, if you're in a room and you spray a little bit of perfume, the vapor molecules of the perfume make their way through the room until they fill up the volume. Right, so that is that process whereby that happens. That is what we call diffusion. Effusion is a little bit different, and that's what we're going to be focusing on in this video. Effusion has to do with the motion of gases through an orifice. So suppose that you have a container, okay, and that container has an orifice. You have gas inside. All right, so effusion is related to the rate at which gas escapes that container through that orifice. Okay. Well, it turns out that people have done experiments to measure these rates of effusion, and Graham's effusion law indicates that the rate of effusion, right, is proportional to the square root of the inverse of the molecular mass of the substance that is effusion. Right, so how you have that this is equal to a constant, and then multiply by the square root of the molar mass of the substance that is effusion. Now what we can then do is try to calculate a ratio of effusion between two different substances. Right, so we could say that the rate of effusion of substance 1 over the rate of effusion of substance 2 is going to be equal to the following. That's going to be a constant square root of 1 over the molar mass of the first substance, and then the same constant square root 1 over the molar mass of the second constant. Okay, these constants are going to cancel, and then when you operate through those square roots, you find that this is equal to the square root of the molar mass of the second gas over the molar mass of the first gas. It's a very simple law. Now what we can do now is to see if we can actually reconcile this with prior knowledge that we have. And what we actually can expect here is that the effusion through this orifice should be somehow related to the velocity that those gases have, such that gas particles that move very fast will effuse faster through the orifice than gas molecules that move much more slowly. All right, so let's actually then try to see if that pans out. Right, so again, what we can say is that the rate of effusion should be directly proportional to the velocity of those gases, right? So we are going to have here a constant. And then from kinetic theory of gases, we actually know what the velocity of a gas is. We can actually quantify that by the root mean square velocity or speed, which is this VRMS. All right, so we want to calculate the rate of effusion of two gases, 1 and 2, or the ratio of those rates. We simply are going to have to divide one over the other. Effusion of gas 2, right, there's going to be exactly the same constant multiplied by the root mean square speed of the second gas. All right, so from kinetic theory of gases, we actually have expressions for these root mean square speeds. These constants go away, and then we can say that this is going to be equal to 3 RT over the molar mass of the first gas, and then the square root of 3 RT over the molar mass of the second gas. Okay, so when you operate, of course, this returns exactly what Graham found. All right, so notice how we can reconcile the experimental measurements, okay, with the theory. Okay, by simply assuming that again the rate of effusion should depend on the velocity that molecules have. All right, so here we can actually then close off this video by calculating, the ratio of the rates of effusion for two normal gases. Okay, suppose now that this is actually a tire. It could be a bicycle tire or a car tire, and then what you would like to do is find out a gas that can actually, when you get a puncture, actually effuses much more slowly through that puncture hole, so that you can actually drive to the gas station if you detect that there's a puncture. right? So generally, when we pump up tires, we actually use air. Okay, and air has a molar mass when it's dry of approximately 29 grams per mole. That is the molar mass. Right, so an idea would be to replace this by something that effuses more slowly. Okay, the rate of effusion is lower, right? So it has to be a gas that is cheap and it should have a larger molar mass. Okay, so one of the candidates could be CO2, okay, which is fairly inexpensive, and the molar mass is larger, 44 grams per mole. All right, so let's then calculate here what the rate of effusion of, say, air with respect to CO2 would be. Okay, so it is going to be the square root of the mass of CO2 over the molar mass of air. Okay, I'm plugging in these numbers that we have right here. Here you will have 44, and here you will have 29 grams per mole. This returns a value of about 1.2. Okay, that means that CO2 diffuses about 20%. Effuses about 20% more slowly than air does. So that will buy you some time in case you get a puncture. Okay, this video has shown the concepts of gas diffusion and gas effusion. And for gas effusion, we've actually seen Graham's law of effusion, and we've been able to reconcile that law with kinetic theory of gases.